Okay, so special Halloween edition of the course today. We are going to talk about statistical significance and related issues today. I think you've all heard of a p-value? Yeah, okay. How many of you could explain what a p-value is? Okay, we've got one. Okay. We're going to beat it to death. And the reason we're going to beat it to death is not so much because I think you're going to do a lot of statistical significance calculations, although you're going to do one in the homework, but because you're going to read a lot of research that uses statistical significance calculations, and you need to know what that means. We used to have an assignment in this course that was read this paper, evaluate this homework, and that's or evaluate the paper. That was a super realistic assignment because you're going to do a lot of that in all likelihood. So this is actually like a sort of Stats 101 lecture in many ways. I'm going to try to introduce you to a different way of doing statistics, which is via randomization, which I think is not only easier to do if you come from a computer science background because it's based on programming and simulation, but also I think it hangs together better conceptually. Yeah, so here we go. The first thing we need to talk about is randomness. Then I'm going to show you a bunch of examples of significance testing. So it actually happens in journalism, and you can use it to detect unusual things that could be indicators of fraud. And there's at least 3 good examples of that. We're going to talk about p-values. We're going to talk about Bayesian statistics and what the difference is between frequentist and betas. And then we're going to go into this idea of p-value hacking and the replicability crisis and what's been called the garden of forking paths, which is a phrase that means that if you get to choose your data analysis method, you can choose different outcomes. And we're building up to a sort of general theory of data interpretation. And I'm going to show you, I'm going to view it through a particular lens, which was actually developed in intelligence analysis called the analysis of competing hypotheses, which is sort of a modern incarnation of an extremely old argument about how to decide what is true. So I really like this class. I think this is like epistemological fundamentals. I think this is basic stuff, and I don't know, it feels hard fought, right? This is the lecture I wish I had when I started studying this stuff 20 years ago. Okay, so we need to talk about randomness. Randomness is a bit of a slippery concept. This is one of my favorite pieces around this idea. And what this is an analysis of the error in the New York Times, or the monthly job figures. So every month, the number of jobs created for that month gets released. It's like 180,000 or something. However, the margin of error is more than 100,000. So let me show you what this looks like. This was one of my favorite pieces, which is basically making the argument that we almost always misinterpret this. So the way they did this is very clever. They basically assumed that the job growth was flat for the whole year and then added in statistical noise to show you all of the different types of patterns that you might see, even though the job growth rate was actually steady. So where's the pause button? Huh, interesting. It looks like this is no longer interactive and they've just replaced it with animated GIFs. Interesting. There used to be a button where you could stop it. But if you look at this for a second, you can imagine if you wait long enough, you will see almost any trend, right? So imagine yourself writing a story about interpreting this trend. Oh, it fell later in the year. Oh, it peaked early in the spring. Oh, it increased at the end of the year. oh, we got a peak and then it fell off in December, right? You can imagine almost any story available just due to noise. Or in this example, here it was actually increasing, but if you wait for a minute there, that's more of a flat trend. Okay? So this is one of the basic statistical problems we need to solve in data interpretation, which is if there is randomness or noise in our data, then we need to know how much, and we need to know whether we're likely to be misled by it. So almost every article that is written about the jobs rate, almost every article that said, it fell by 50,000 and analysts sold off stocks as a result, almost all of them are probably wrong because you're well inside the noise. And by the way, the noise here comes from, it's just sampling error. So what you're actually doing when you compute the job growth numbers is you take the result of the monthly employment survey, which is, well, there's actually two. There's a household survey and there's a company survey. I forget which one they use for this. I think it's the household survey. So that's a big monthly random sample. And so then you get some number, you say, okay, the labor force is 120 million or something. And then next month it's 120 million.1, and you subtract the two, and that's the job growth rate. The reason the noise is so large is because you take this huge random sample and you get, maybe a 1% margin of error. Well, 1% on 100 million is a million. So actually you can see that they do a lot better than 1%. So what you're seeing is the noise that results from subtracting two very large numbers. Which reminds me of one of my very favorite pieces of financial journalism. Bank of America, Matt Levine. Let's see if I can find it. Yeah. Bank of America made 168 million last quarter, more or less. So this is Matt Levine at Bloomberg, who's a fantastic financial journalist. And the point he's making here is that 168 million is a rounding error on their income, depending on the accounting standards they use, depending on whether they're counting certain things this year or next year. I mean, you can't even tell if they were profitable or not, right? And this is not even statistical error. This is just the rules about how to count this are very complicated. And the reason this is complicated is because you're looking at very small percentages of very large numbers. So it's the same situation as the job report. There you go. Bank of America's earnings are a rounding error. So when you're thinking about two large numbers and comparing two large numbers, the difference is going to be incredibly noisy. Because that's what you're doing here. You're comparing this year's earnings to last year's earnings. And because there's so much variance just in getting this number, the difference is not that interesting. Okay, so that's the idea of variation. We're going to talk a little bit more about randomness. So if I show you these two pictures, which one do you think has random placement of the stars? How many for the left? Okay, how many for the right? Oh, all of you on the left, good. I feel like my students are getting smarter over the years. Okay, in fact, the one on the right is less random in some sense because it broke it down into grids. So we might think of randomness as sort of unpatterned, but randomness actually has a lot of pattern in it, right? Think of think of all of the different ways that you can have 12 months of job growth. Most of those ways show some sort of pattern. So here's another quiz. Here is some data, and 8 of them are randomly generated values, and 1 of them shows an actual statistical trend. Which one do you think is the real one? Any guesses?
There's not really much of a way to guess, but if I had to guess, I would probably go with top center.
Top center. Why?
Because it seems to match a curve pretty nicely.
Okay. Any other guesses?
The bottom, right.
Bottom right?
Yeah.
It's a nice decreasing trend. Yeah, actually they're all random data, right? So the point I'm trying to make here is that if you're looking for a pattern in noise, you will find it. So whether you see a pattern or not is not the interesting thing, right? That's not the criterion we're going by if we're going to do inference from data. Another principle I'm going to try to get across is that when you have less data, the problem is more severe. So here's the same thing again. I've just generated a bunch of random points and drawn regression lines through them. Notice that compared to when we have less data, the lines here are a bit flatter. And this is a basic statistical principle, which is that if what you're looking at is noise, the more of it you have, the easier it is to tell that it's noise. Right? When you get small samples, it's much easier to see a pattern. And we get very small samples all the time, right? So let's say we're talking about the number of homicides in Chicago and whether it's going up or down. So you do some story and you're like, well, look at the last 5 years of data. It's a lot higher it was now last year than it was 5 years ago. That's only 5 data points. If there's any sort of random variation in that, it's very likely that it's going to completely swamp the actual data. This is part of the problem with trying to do these sorts of comparisons, is you have very little data. So this again, this is like Stats 101 stuff, and I expect you've all seen some version of this, right? But here are sort of the basic issues that we're going to have to try to deal with, and this is why statistical significance was invented. So we try not to fool ourselves by seeing patterns in randomness. And in particular, this is a bigger deal when you have less data. The easiest way to start talking about statistical significance is going back to this classic type of statistical question. And this has been people have been talking about this for hundreds of years. Here we have a histogram of die rolls, which I just built in R using the code at the bottom. We roll the die 60 times, so we should get 10 for each, but we get, looks like 13 or 14 for 2. Is this die weighted towards a 2? What do you think? No? Okay. Is there a principled way to answer the question? So there's a lot of different versions of this question. One of the most famous ones, which was proposed by a statistician named Fisher, is called the lady tasting tea problem. And the problem is this. So any Brits among us? No, okay. So apparently, Brits feel very strongly about the order in which you put the tea and the milk. And I can't remember if it's milk before tea or tea before milk at this point. But let's say you prepare a bunch of cups of tea, half of which have tea before milk and half of which have milk before tea. And then you bring in an aristocratic woman and you say, please taste this tea and I'm going to give you either all milk before tea or all tea before milk, and I want you to tell me which order you think each cup is. And the question is, how many times does she have to, sorry, you're not going to give her all, you're going to give her, each cup is going to be one or the other, right? You're going to give her randomly each cup, either milk before tea or tea before milk, and she has to guess which one it is. How many times does she have to be right before you start to think, oh yeah, she really can tell the difference? This really does make a difference. Because, she can get 3 right guesses, 1 out of every 8 shots, right? What if she has 3 right guesses and 2 wrong guesses? How often does that happen? So it's the same type of problem. So in order to answer these types of questions, so here's another one. How about this one? Do you think this is a loaded die, or do you think this is a fair die?
I still say it's fair.
Okay. So you still say it's fair. Okay, so, I know the answer because I wrote the code. So I either did 60 die rolls and just kept doing it until I saw this, or I made it overweight the ones and did it once, right? So which one did I do?
Well, now that you said you wrote it,
Yeah, I made this.
and I don't think you're going to be sitting there for hours trying to get this result, I'd say it's loaded.
So would it take hours to get this?
No.
How many rolls would it take to get that? Or how many sets of rolls? Because each of these is actually 60 die rolls. Okay, so clearly the answer depends on not only the difference that I observe, but the how often I would get that difference by chance. Right, so we're building up to sort of the basic statistical framework behind significance testing, and in fact, all kinds of statistical work here. Now I roll the die 60,000 times, okay? And I get a very small difference. I'm looking at it's still about a 10% difference. So the difference is about the same as this one, right? It's not much, it's a little bit smaller. But what do you think? Is this a loaded die?
Yeah.
Yes.
Okay. So why are you so certain for this one?
Much larger sample size.
Which means what? Why is the larger sample size relevant?
It means you've tried enough and it's still loaded. I don't know how else to put it.
Well, look at this stuff. This is relatively flat, right? Why is it relatively flat? Yeah, when you have a larger sample size, your averages have less noise. Okay, and these are really all averages, right? I'm just counting how many times I get each one. So this is the average number of rolls that got a 3. So you can start to see, I hope, how these factors play into each other, and we're going to make this more precise in a second. With 1 die, we have a flat distribution. With 2 die, we have a non-uniform distribution. We can derive the distribution analytically by just counting how many ways we have to roll each number. Right? You can usually, for simple problems, you can just compute the results combinatorically. It's basically just a symmetry principle. You just say, well, the number of times we expect to get a 2 on the white die is the same as the number of times we expect to get a 4. And so we just run through all of the possible combinations that way. When we actually simulate it, the histograms don't look anything as clean. I think here I've got another 60 rolls or something. And so you can see they're a bit all over the place with samples this small. And if you only do 60 rolls, and this one is rigged to give 2 5s, for example, let's say that's why we get all this 10, it may be very hard to tell that something is wrong with the die until you roll it hundreds of times. There are cases, so So far we've talked about cases where there's an analytical solution. You can sit there with some algebra and figure out what the fair distribution looks like. When you're doing your actual data analysis, or if you're doing some sort of data visualization, you may not have an analytical answer to what noise is going to look like, right? That's kind of the question we're answering by doing these simulations, is what does noise look like? So this is from a beautiful paper which is in the readings, which sort of pulls out a lot of these statistical ideas into a visualization framework. And here we're showing cancer rate per county. And what we've done in this image is one of these is the real data. The rest are synthetic data generated by taking the original cancer rates and scrambling the counties, okay? So this is our first instance of generating a null hypothesis by randomization. So I'm introducing a couple ideas here, right? First is null hypothesis. And what that means is you can think of this colloquially as the data is just noise, okay? Our theory is that what we're looking at, there's actually no pattern in the sense that we care about. The die is fair. There's no relation between location and cancer rate. There's no difference between the two classes. The jobs rate was flat. You know, whatever it is, we're saying that the actual pattern we see is just noise in some way. And then the other idea we're introducing is randomization. And we're using randomization to generate examples of what the data looks like under the null hypothesis. So we've already been doing this. When we do this type of thing, what we're using is we're using a model of the null hypothesis, right? We're just rolling two fair die and adding them. When we do this, the way we make the model is, okay, so we have some counties. This is what our data looks like. And each of these counties has a certain cancer rate. And then what we do is, the null hypothesis is that there's actually no association between where the county is or which county it is and what the cancer rate is. So we permute this distribution, right? We say, oh, yeah, let's just scramble them a little bit. Okay? All we do is we randomly reorder these things, or in the case of our county data here, we just swap all the counties around. And what we get is something that has the same distribution of underlying rates. So if you draw a histogram of the county data, you see exactly the same thing. We haven't changed the data. But if you map this stuff, what you see is this. Right? What you see is some of the data that we could see if there was no relation between where the county is and the cancer rate. So then the question is, can we tell which is the real data and which is the synthetic data? Because if we can't tell the two apart, then the pattern that we're seeing in the real data is a pattern that happens just by chance. And it's much less likely to be meaningful. So, anyone want to take a guess what the real data is?
3. I think it's 3.
Yeah, everyone said 3? 3 is correct. So the fact that you could correctly guess which was the real data means that there is actually geographic pattern here that is distinguishable, and looks like fairly accurately distinguishable from random data. Okay? So you have all just provided statistical evidence that something is happening that is not random. I think we looked at this earlier when we were discussing text analysis. This is This is an analysis of the anachronisms in Downton Abbey. Did we talk about this earlier? Yeah, okay. So on the horizontal axis so it's taking every two-word phrase in the scripts of Downton Abbey and first of all, plotting the overall frequency. It's on a log scale. So 10 to the minus 1 means every 10th bigram is this. I think that can't be quite right because 10 to the 0 would be every bigram is this. Anyway, something like that though, right? So the more common words go to the right. And the vertical axis is how much more commonly we see this in the Downton Abbey scripts than in Google Books results from the same time period, right? So 0 here, so it's the log of the ratio. So 0 means we see it at the same amount. So of course you see everything clustered around 0, which means the language is broadly the same. And then this stuff up here, right, all of the stuff that starts to get high on this chart is overrepresented, right? So 2 here, that means we see this 100 times more often, we see about 100 times more often in the Downton Abbey scripts than in the books corpus. Now, the question I want to put to you is, what would be the shape of this scatter plot if actually the language in Downton Abbey is drawn from the same distribution as the language in Google Books? So that's our null hypothesis here, right? So null hypothesis, and I'm being a little more technical here. Abbey's scripts from same word distribution as Google Books of the same era, right? I don't know. It's around World War I. I'm not sure exactly which years he used. So think about it this way, rather than trying to, so you can do an analytical analysis, right? So you can algebraically work this out, but I don't want to. So let's imagine simulating this. How can we make a simulated version of this chart? So think of this as making fake Downton Abbey scripts. Any guesses? Let's generate some Downton Abbey scripts that are drawn from the same distribution as the words that are stored in Google Books. How do we do that? We don't need to read the scripts. They don't need to make any sense. They're just... Yeah, so if there's 100,000 words in the Downton Abbey scripts, then let's sample 100,000 bigrams from the Google Books corpus, which we can do, by the way. You can download the frequency tables for Google Books for each year for up to 5 grams, right? So we can just download the data and do this, okay? So we can generate fake data, and then we can produce this plot. And we just do that by then basically just comparing the sample that we have to the Google Books baseline, and we can generate this stuff, right? So we take each bigram, we say, okay, how many times did we choose it in our scripts, which gives us the x-axis, and how many times do we have it in as compared to in Google Books, which gives us the y-axis, and we go. And so when we do that, we will get a certain shape. And I want you to think about what that shape might be. What shape would we see for this chart? Any guesses?
It would be like, it would have frequency going over the entire space, ideally.
Right, okay, yes.
It would be like, the ratio would be the same because you're saying that you're taking from the same source.
Right, okay, so good. So good guess. That's a good start, right? So the 0 line is means the ratio is the same because log 1 is 0, right? So because we pull them from the same distribution, we should get stuff around this 0 line. But we're not quite going to get stuff around this 0 line. What's that?
Yeah, I'm not understanding the random part of it, I guess.
like how we generated the.
If it's matching the trends of the Google Books, where does the randomness come in?
Well, because we're not going to, because the Google Books is this huge big distribution.
Oh.
If we sample a certain number of words, some words are going to appear more often by chance. Some words we're never going to sample.
Are we just taking a random sample?
Yeah.
Oh.
Yeah. So,
Because the script has this,
Yeah.
sometimes you might choose a book that has the word black market too many times and end up sampling from it too many times because it's random. And then
Right.
the black market rates are way up high, but in actuality, it's still there.
yeah, the randomness is how often did we pick this word, right? So if we by chance picked a word a lot, it'll be up here. If we didn't pick a word very much, it'll be down here.
Is the overall frequency there in the Downton Abbey scripts or in the Google Books?
I think it's in Google Books. Yeah, I'm not sure though. Okay, so here's the thing though. We're going to get this sort of funnel shape. And the reason we're going to get this type of funnel shape, it's going to sort of walk up the chart here. It's going to be denser in here, but it's going to sort of go up here. And the reason is because these are very rare words, right? So think about it. If a word appears once in every, or I'm just going to say word, it's actually bigrams. If a word appears once in every 100,000 words, okay, and we have one in our script of 100,000 words, then we're going to be on the 0 line. But say by chance we pick it twice, well now it's twice as often. So it's going to go up here. So the rarer the word is, the more difference choosing that word a single time makes on the vertical axis of the chart. Another way to think of this is as we go to the left of the chart, we get a smaller sample size. Because remember, we're comparing the ratio of two samples. This is the sample in Google Books, this is the sample in the script. Right? If the samples are very small, we're going to get a lot more noise. So if you actually do this experiment, you will get a shape that looks like this. And so if we interpret this chart, we have to sort of imagine that there's a curve which runs kind of like this, and we're really only interested in the stuff above the curve. In fact, what we could do is we could numerically calculate what is the curve that represents we only get a value this high 1 out of every 100 samples. So you see this characteristic type of funnel shape in a lot of cases. So for example, if you take school test data where you have the average test score for the class and you have the class size, and you plot class size on the horizontal axis and test score on the vertical axis, the smaller classes will have the most extreme values. If you plot crime rate per county, well, crime rate is a ratio, right? It's how many crimes versus how many people. If you have a smaller population in the county, one murder can make the crime rate incredibly high, right? That one crime has a much larger effect on the rate. So anytime you're taking averages or rates, when you have a smaller group of people, you get a lot more noise. Which means, and this is a classic trap, you know, the classic story is you download the crime rate data and you say, oh, which county has the highest rate of car theft? You know what? It's going to be one of the smallest counties. Always. Because it just, or most likely, because it just has the most noise. So when you're analyzing this, any type of data which has some sort of noise or random process in it, that first question you have to ask is, what does this look like if there is no pattern? Which means you have to figure out what no pattern means. And for the example we just did, no pattern means, I just defined it to mean the same distribution as Google Books of the era. Here's another example. This is from The Signal and the Noise, which is Nate Silver's book on prediction. And what he's talking about is the claim that, hey, look, the temperature rise stopped. I think now we have data almost 10 years later and it's going up again. But in 2010, people were saying like, oh yeah, global warming has stopped, look, right? It's been flat over the last 10 years. But you can see there's variation here. The biggest variation, by the way, is the 11-year sunspot cycle. So there is actual astronomical sources of variation here as well. On multiple timescales, there's some like 100,000 year cycles as well. So he posed the question, how often are we going to see a flat decade even if the temperature is actually going up? So how would you answer that from this data? Any guesses? What's that?
Every decade is so.
Well, some decades are going up, right? There's a general upward trend, right? So that's going up, that's going up. But this is a flat decade, that's a flat decade, that's a flat decade, that's a flat decade, that's a flat decade. So what he did is he said, okay, well, how often do we see a flat or decreasing decade just from that data? So in this case, he's just using the data itself to get an estimate of how likely it is. Because we look at this and we know there's a general upward trend, right? So there's definitely a long-term upward trend. And what he's saying here is, even with this general upward trend, you're very often going to see decade-long decreases in temperature. So seeing a decade-long decrease in temperature doesn't mean that the upward trend has stopped.
So writing anything like greatest or worst in the last decade is not okay.
Writing what?
Like writing something to the effect of like, oh, this is the greatest or the worst temperature in the last decade is not fact.
No, you can say, that's totally factual. You can say that this is the greatest temperature in the last decade, right? But to say that, the temperature trend in the last decade has been flat, therefore global warming has stopped, that's not sensical, because we can see just from the historical record that it appears that there are decreasing trends on the timescale of a decade fairly often. And yet we know, because we have the data subsequent, that this decreasing trend was not the end of global warming. Okay? So I hope you're seeing the sort of conceptual connection between all these examples. Okay, they all rely on the idea of how often does the thing I'm looking for happen by chance, given the inherent structure of the underlying data. So, here's another example. This is what I call the lottery fallacy. This is also due to Nate Silver. Where was this? 1976. There was thought that there was going to be a big flu epidemic, and so there was a huge vaccination program, and some of the people who had the vaccine died. But 3 people who were vaccinated in one clinic in Pittsburgh within the same hour all died that day. So, this is the same structure as is the diluted. Doesn't make a difference to if you put the milk or the tea in first. Do we see a pattern in the cancer rates here, right? Look at the structure of this argument. It is extremely improbable that such a group of deaths should take place in such a peculiar cluster by pure coincidence. That's the argument, right? It's the same structure of the argument. This is not chance. The null hypothesis is wrong. Or another way to say this is, the null hypothesis in this case would be something like, the vaccine is safe, they died from something else. This editorial is explicitly saying the null hypothesis does not generate the observed data with high enough probability. So Nate Silver, being Nate Silver, said, okay, let's calculate how high the probability is. So here you go. Here's what he did. Basically, he takes the death rates for elderly Americans, which he defines 65 or older. He asks how many elderly people visited a vaccine clinic. He makes an estimate of the number of clinics, converts that to how often, just the chance of any one person dying, and then to how the chance of 3 people dying, and there you go. So this is probably what the person who made the argument, the editorial argument, was thinking about 480,000 to 1. Right, so it's very unlikely that 3 people who went to the same clinic in the same day will die from some other cause. However, there are 5,000 clinics to do this, and 11 days over which this happened. So when you put that all together, the odds are about 1 in 9, right? So greater than 10%. So here he's making the opposite argument. He's saying, no, this is not extremely improbable. This is about 1 in 10. Which, now we have the problem of, well, do we think the vaccine is safe or not? What do you think? Is a 1 in 10 chance of this happening by chance? Does that suggest that there's a problem with the vaccine, or does it suggest that the vaccine is probably safe?
Probably wouldn't want to get the vaccine at that particular clinic. Those kinds of thoughts.
So what you're doing there is you're invoking a different hypothesis, and you're saying it's not a problem with the vaccine in general, it's the problem with the vaccine at that clinic, or something about what that clinic is doing. Yeah, that's a reasonable alternative. In fact, let's start writing these down, right? So null hypothesis is...
Maybe they all bought meats at the grocery store that they went to.
Right.
Got the vaccine and had food poisoning.
Null hypothesis vaccine is safe. Let's call this H1. Clinic is bad. H2. Vaccine is bad. H3. Food poisoning. Right? And we can go on. Now we're starting to get into what we're going to look at the end of the class, which is the analysis of competing hypotheses. And the question we can ask is, how often will this hypothesis generate our real data? Okay? So we have some real data, in this case 3 deaths in 1 day, or we have some real data, in this case, this word cloud, or these images. There's always some data that we observe. And the question we're asking is, for all of the hypotheses that might be causing this, how often will it generate the data? Now, this is a purely statistical question. The answer will be phrased in terms of probabilities or ratios of probabilities and so forth. That is a different question than should we investigate the safety of the vaccine. This is the difference between probability and decision theory. Probability gives you a chance of something happening. Decision theory tells you, well, what choice should I make? And decision theory introduces costs, okay? It introduces the idea of an expected value, expected benefit, expected loss, expected utility. And although the probability that the vaccine is bad might be very low. The cost of having the bad vaccine is enormous. So the expected value calculation becomes very large. This is similar to our issue with setting the threshold, false negatives and false positives, for releasing people on bail pre-trial. Where you want to set that threshold depends on what you consider the cost of a false negative versus the cost of a false positive. So how much worse is it to keep someone in jail who wouldn't have committed a crime versus release someone in jail who then goes on to assault someone, right? How do you weigh those? So probabilities themselves cannot tell you what to do. You have to combine them with costs. So this is sort of the first step in a decision analysis. Because the thing is this, right? Even if we have a very small chance that the vaccine is bad, because the potential outcomes of having a bad vaccine and not handling that situation are so costly, even if this probability is very small, you still want to investigate it, maybe stop vaccinating people. So so going back to this editorial, right? I'm not even saying that this person is substantively wrong, right? They're arguing here that we should probably be careful with this vaccine. I'm saying that their argument that it's unlikely is not really true, because there's a lot of chances for it to happen. Okay. Thoughts on all this stuff? Questions?
Well, which is journalism closer to? The idea that, like, the hypothesis too, because it is so bad if it were true, it's worth investigating.
Yeah, no, I mean, I would say this is definitely a reason to investigate that possibility. However,
Does that mean it's a story? Does that mean that the bar for something being a story is lower?
So what I'm saying is that if you're going to argue that something is improbable by chance, put a number on it. Right? Actually think about it. Is it that unlikely?
Are our audiences numerate enough to have that be meaningful for them without further interpretation?
Potentially not, but you are. Right? So that's something you need to think about.
So what do we step, like a fact check? Are we really saying this unless we know what the numbers mean?
What's that?
It's more like a fact check from our end of like, how can we say this without a number?
Yeah, I mean, you may or may not want to publish the calculation. It's probably better if you can rely on an expert in that field to do these types of calculations. But when you start looking for this, you see it a lot, right? What you see is the argument that something couldn't possibly happen by chance. And almost always when someone says that, they haven't actually estimated the probabilities. Okay. So we're zeroing in on the idea of statistical significance, which is this idea of arguing that something must be true because the alternative is very unlikely. So this is the earliest example I can find. This was the Howland-Will trial. Sylvia Ann Howland was a rich American aristocrat who died in the 19th century. And there was an addendum to her will that said that all of her money went to her niece. And this is an original signature that they know was real, or at least it was undisputed in the case. These are the two signatures on the addendum, and the argument was that her niece forged this stuff. And to prove this, the prosecutor hired Charles Sanders Peirce, who is best known as the inventor of the randomized controlled experiment and one of the founding philosophers behind pragmatism. He was a great 19th century scientific epistemologist, and asked him to compute how likely it would be that these were forged. And the way he did it is he took 41, I think, pairs of signatures. Do I have this? No, I don't have the text here. But late 19th century. And so I have this story in Curious Journalist. So, arguing from the odds. Yeah, so he took 42 signatures that the court believed to be genuine. And he was actually, Pierce Senior actually did this. And he printed them out on transparent photographic plates, and he overlaid every possible pairs, which is 861 possible pairs, and asked how often. He broke the signature into 30 individual strokes, downward strokes. So that's a stroke, 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 right? And he asked how often were the strokes had the same length and horizontal position. And he found that the same stroke matched only a fifth of the time. So he said that, well, for 30 strokes to match, which the disputed signature did match exactly, happens by chance only once in 5 to the 30. Okay? So now this is not, there are problems with this statistical argument, but this gives us sort of a ballpark. So his argument was that it is very unlikely that if Sylvia Ann Howland signed her name, that she would sign it exactly the same on 2 different documents. And we know that from looking at the variations on her real signatures. So again, what she's saying is, so in this case, the null hypothesis is, which is normally called H0, is it's an original signature, and H1 is forged by copying, right? So by tracing it. And what he's trying to do is calculate how often the null hypothesis replicates the data. And he's saying, well, it's super rare. So this same basic form appears over and over, and it is the fundamental concept in hypothesis testing. And it's a little bit of a weird thing, right? Because what you actually care about is proving this guy. But to try to prove this, what we do is we say, well, the alternative is that, and the alternative is super unlikely. And people have done this in journalism. So the Wall Street Journal has won a Pulitzer Prize and actually done 3 different versions of this story over 10 years, looking for various types of insider trading. So insider trading is when an executive in a company has information that is not public and trades stock based on that information. There are laws about this. For example, there are blackout periods before and after earnings announcements where executives and often other employees can't trade during those periods. To answer the question of whether people were, or to try to find insider trading, what they did is they took the executives of a bunch of different companies and they looked for cases where they sold a bunch of stock and made a bunch of money right before the stock changed value. Bought stock before it went up, sold stock before it went down. And in this particular country context, what they used are backdated stock options. This is an instrument where they grant them some stock options, but then later they decide, oh, they were active as of this date. And so the question is, did they really pick the date just arbitrarily, or did they pick the date sometime later and set it at a date where they would make a lot of money? And to answer that question, what they did is they took all of the trades and did thousands of simulations to see how much they would normally make if the trades were on random dates. So here, breaking this down a little bit. So they looked at people who are using this type of stock option, and they're finding that they make a lot of money. But the people who don't do that, use that type of stock option, don't make as much money. And let me show you how this works. Oh no. Google tends to ask for my password at awkward. Really? Why does it randomly pick my...
New.
It's not new at all. Okay. Yeah. So this is a nice discussion, which I will post to the course Slack, in how this works. And it explains how this analysis worked. So first of all, they looked for news that changed the stock price. And then they looked at who sold stock the week before. And they found that 10% of them made a bunch of money. But the problem is, sometimes you're just going to make money anyway because the stock is going up, right? Or down. So instead what they did is simulation. So what they did is they broke the link between the trades and the timing of the trades. So they took the same trade, I sold this many shares, and they said, okay, rather than it happening on this date before the news, let's pick a random day in the year, and let's see how often you make this amount of money if there's no connection to the timing of the news. And what they were able to show is that if this was just luck, they were incredibly lucky. They did these simulations and they found minute chances of making this amount of money from the stock trade. It's the same thing we've been talking about, this randomization approach. So now, instead of randomizing the link between cancer rates and county, we're randomizing the date of the stock sale and asking how often do I make this much money on a random day. Now, is this evidence of insider trading? How do we handle this result as journalists? This is the complicated part.
Can you look at what kind of news it is? Maybe like instances where it was like the news itself was something that doesn't have an outcome, and having that information would have made it even more advantageous for them.
So you're saying that if
Go ahead.
the news is particularly unusual, then that means they're even luckier?
If it's guidance information that's not usually spotted
Okay.
on his report, and knowing that anybody would have changed their mind, but this was even more.
So really what I'm asking here is, so say we do this, we identify, this person. Okay? And, they made an extremely improbable amount of money if they were just trading randomly. Right? So we think, okay, this is not a random pattern. Can we write a story saying that they traded on non-public information? No. Okay, why not?
Still got to be a journalist.
Still got to be a journalist. What does that mean?
Just a statistician.
Yeah.
It's got to corroborate your findings.
Right, so remember, insider trading is a criminal offense. You can't accuse someone of a criminal offense without proof, right? And usually, you don't accuse someone of a criminal offense unless they've been convicted by a court. If they've been accused but not convicted, you say, allegedly, or you hedge it in various you hedge it in various ways. But that's not even that, right? The SEC has not opened an investigation against them, right? There's nothing going on here except the statistical result. So you can't call them a criminal, right? You can't say that. But
You can
what do you
what
say
they
instead?
what they did here, which is just report the facts, and as a reader, it's unlikely that the executives didn't know about an earnings report or an unfavorable story about drilling or whatever the
Mm-hmm.
news revelation was. So it's not like they are decoupled from the news, but you're still not making a accusation.
You're right, and in fact, I love how they handled this. Look at this headline: "Executives' good luck in trading own stock." Right? They didn't accuse them of any wrong. The only thing they said is they had very good luck. And the thing about this is that it may be true. Some of these people probably just traded randomly and got lucky. But not all of them. It's just too unlikely that they all got that lucky. The problem is we don't know which ones were lucky. A small number of them will have just been lucky. Probably most of them it is some sort of inside information. Whether that's illegal or even immoral, it depends on the specifics, right? That's a question of law, not statistics. Right? There's all kinds of complicated law about whether it's insider trading or not. But they actually did 3 different versions of this. They did it with trading before press releases, they did it with backdated stop options, and they did it with one other type of investment vehicle. So they've actually done this story multiple times over 10 years with about the same statistical technique. Another nice example of this is the tennis racket, which was a story that BuzzFeed did recently. And this was the part of a much larger investigation into match fixing in tennis. And what they did is they took public betting odds, right? They scraped it from a bunch of betting sites, and they looked at cases where the odds shifted dramatically between the start of the match and later on in the match. Right? And the idea there was that if someone was heavily favored to win and they lost, maybe they threw the match. Or, as they put it, if bets come in against a favored player, maybe that's evidence of match fixing. So BuzzFeed actually published the code for this. It's a pretty straightforward simulation. And what they did is they generated a list of, I think, 15 players who frequently paid matches where the odds shifted a large amount. And they didn't actually publish the names of these players. They just said, we found a bunch. They did publish the algorithm to do it, and the data is publicly available. So some readers promptly ran the code on the data and got the names. So interestingly, again, they didn't even publish the names. They didn't want to accuse people of match fixing based on this type of evidence alone. Why? What is the weakness of this type of analysis?
They could have just had a bad day.
Yeah, they could have had a bad day for all kinds of reasons. And there's a really nice article. This is also in your readings. This is a very, where are we? Okay, so here's the original. How they use data to investigate match fixing in tennis. And here's a lovely article, Why Betting Data Alone Can't Identify Match Fixers in Tennis. And this is a beautiful critique of the method. And one of the things that they talk about is what are all of the other ways that a player can tank a match. So it's the same sort of concept, right? Null hypothesis through the match. And then the alternate hypotheses deliberately losing.
Oh.
Yeah. The alternate hypotheses are things like H1. Bettors have inside information. H2. The betting markets are wrong. And so the example it gives there is maybe there's a recent injury that the bookie doesn't take into account, for example. That's what he's saying there. And then this is very interesting. H3 is, let's call it methodological problems. And we're going to talk about this a lot when we talk about the Garden of Forking Paths. So check this out. What 538 did for this article is they hired a statistician to replicate the results. And they did it a little bit differently. First of all, he used a few more matches, okay? But also, the BuzzFeed analysis looked at the bookmaker, right? So there's 7 different companies producing betting odds, and they're going to have different odds for the match. And what the BuzzFeed analysis did is took the bookmaker that showed the maximum movement in the odds, whereas Sackman took the median of the odds given by the bookmakers and looked at how much the median moved. So that's a different methodological choice. Why would that be justifiable, by the way? Why would you think, well, maybe I should use the median of the odds rather than just the maximum of all of them? Why would you want to do that?
You're trying to control for like extreme
Yeah.
values.
Right, so the median removes extreme values, right? So if you take the median of all of the bookmakers, basically you're just throwing out the data for, the bookmakers who just got it stupid wrong, made a stupid mistake, were having a bad day, didn't take into account the data in the right way. There can be data errors as well, right? There can be typos. You're just throwing out all of that stuff, right? And when you use the median, you get a much smaller number of players who have suspicious odds movements. So he made a bunch of changes.
But wouldn't match fixing only concern individual bookmakers?
No,
Or the whole market?
No, it's going to be the whole market because the idea is that the player deliberately chooses to lose the game. and is being paid off by bettors who are betting against a player who is favored, right? So everyone thinks he's going to win. You say, I'm betting that he's going to lose. You get very good odds on that, right? It pays back, let's say, 10 to 1. Then the player loses, and you make a whole bunch of money, and the player is in on it, right? They get part of the winnings, right? That's why it's illegal.
Right.
Okay?
But wouldn't you pick bookmakers that had like extremely favorable odds? Anyways, like when you always pick.
Oh, I see.
Bookmaker,
You pick the bookie who's the most pessimistic because you get the best odds.
Yeah.
Yeah, probably. That's a good question. But so that's where the money would go. But for this analysis, basically the whole concept of the analysis is you look at cases where the odds shifted very rapidly once they started playing, indicating that they seems to be very unlikely to lose, and yet they were losing. Anyway, when you make this methodological change, you get a different set of names and a smaller set of names. As he said, according to the statistical significance threshold that the original analysis used, only one player, not 4, were above this threshold. So when we change the method, we get a different result. And that's an indication that we have methodological issues. What you hope for is a result where when you change the method, you get the same answer. That's known as a robust result. And this is true not just in statistics, by the way. This is true in journalism in general. So then BuzzFeed's analysis there you go. So this is how BuzzFeed handled this. They said, first of all, we're not claiming that by itself this analysis proves match fixing. But they said, okay, but we also had this whole other investigation, right? The statistical analysis was only one part of the investigation. And they also noted that 6 of the, I think, 14 players they found were also under investigation. So there's some reason to believe that the analysis was effective in finding the people, although, again, you have the same problem. It's hard to make the argument that any particular player is cheating based on this. So I'm going to show you, okay, thoughts on this? Again, it's exactly the same structure of the argument. We're saying that so actually I got this wrong. The null hypothesis is not that they threw the match. That's I don't know, let's call that HF for fixing. The null hypothesis is, let's say, lost by chance. And how they generated data to see if they lost by chance is they simulated all of these games. They took the initial odds and they said, let's simulate 1 million games and see how often this player would lose as badly as they did. And they said, well, that doesn't happen very often, so we think it's evidence of this. And then 538 is coming back and saying, okay, but why is it evidence of that and not evidence of this or this or this? So this is the basic weakness of the statistical significance argument. The statistical significance argument has got a very funny structure. It always says the alternative is unlikely, Therefore, my proposal is correct. Okay? And in a certain sense, that has to be true because if we give a probability to every hypothesis, right? So let's say P0 is the probability of match fixing, P1 equals probability of injury, etc., right? And then let me relabel this. P1 is match fixing, P2 is injury. P0 equals, we saw the results that we saw in the odd shift by chance. We know that P0 plus P1 plus P2 plus all of the other possibilities equals 1. That's an axiom of probability. If we could list out every possible option, they have to sum to 1. So if this is very small, then these have to be big. Okay? So the structure of the argument does make sense formally. If it's very unlikely that the null hypothesis produced the data that we saw, then that is evidence that something else produced it. The question is, how many different things could have produced it? And the difficulty with the structure of the BuzzFeed argument is they're saying, well, it must have been this. And BuzzFeed is saying, well, hang on, there's all of these other possibilities. If there's only one other possibility, so think of the Howland-Will trial. Either it's fake or it's real. And if it's very unlikely that we see a signature by that, like that, that is a real signature, then it has to be a fake signature. Okay? But in the tennis fixing case and in the insider trading case, we have other possibilities. So all we know is that we can exclude chance, but now we don't know which of the other ones it actually is. One of the things you can do to understand whether statistical significance testing is going to, or what kind of evidence it provides, is to talk to other people who have done it. So this is again from that 538 story, right? And they talked to this guy who, gave them this quote about what it meant. And also I find this really interesting. Doing the same thing has proven problematic in other sports. So that feels like one of those sentences where the reporter knows a lot. They probably have like pages of interview notes and like interesting links, but they haven't given it to us.
Team sports, for instance.
Yeah, I'm sure there's a long history of trying to detect cheating through statistical methods. And you see this in elections as well. We're not really going to talk about that today, but you can see the election fraud in the Russian elections by looking at the results in a bunch of different ways. One of the ways you can see it is if you do a histogram of the precinct counts, way too many of them end in 0 or 5. You know, so 65%, 70%, 75% for Putin's party. People are very bad at making up random numbers. Pick a random number between 1 and 10, all of you.
5.
How many of you chose 7?
I did. I don't believe in free will.
That's right. It's because I decided you would take 7. Okay. Rounding out our discussion of what I'm going to call pure significance testing. You'll see why in a second. This is a fascinating article, which was originally on Medium. And this was about someone discovered that there were a series of payments just before October 28, 2016, which was the date of the contract between Stormy Daniels and Trump. There were a bunch of campaign finance payments that totaled almost exactly 130,000. And so then this person did an analysis, and what they did was the same sort of randomization technique, right? They said the null hypothesis is these are just random payments, and how they generated instances of the null hypothesis was they just randomly sampled from all of the payments in the previous month or so. And they asked how often, if I randomly sample 10 payments, do I get a bunch of them that get to near 130,000. And here's what they did. They found this thing and they said, whoops, we get to within, 1% of the time we get to within $2.75. And that was their argument, that these campaign finance payments were actually the payments to Stormy Daniels. Now there's some problems with this argument. This is a great example of, you sort of have to think through the argument, right? Like, what are the possibilities other than it was a payoff? Well, chance is one of them. Were there recurring payments that totaled $130,000? Are these numbers accurate, or are they changed later? And then you get into this whole issue of, if you're trying to hide payments by the campaign, is this how you do it? This is how campaigns have done it in the past? There's all of these other issues, aside from the statistical issues. But it's the same idea. And so finally, we get to p-values, which are one of the most widely misunderstood concepts, most widely used and most least understood concepts in statistics. And that's a formal definition. Let's try this informally. Anybody want to hazard an explanation of what a p-value is? Our resident statistician.
If you have a null hypothesis and another hypothesis, the p-value just, the way that they did in the previous example, it talks about the probability that, that your alternative is significant enough for it to not be false.
Yeah, okay, so it's a complicated idea. It's actually a little weird. So here's the sort of standard definition. The idea is that we have something called a test statistic, which measures how out there is our answer, right? So, if we're looking at the change in jobs and we're like, oh, look at that changed by 100K. The test statistic is maybe, how many standard deviations away from last month are we? The test statistic is often turned into a z-score, which is a difference expressed in standard deviations, but it can be really anything. The fundamental concept of a p-value is p-value probability that we would get data at least, and I'm being a little informal here, at least as extreme as our real data, right? So I'm differentiating here between the data we observe in the world and the data we're simulating, at least as extreme as our real data, if the null hypothesis is true. So, generally for the sort of standard statistic is the general threshold is p smaller than 0.05, so 5% chance. But this definition is complicated. If we have a p-value of 0.05 for, is there a difference between these two drugs? Is there a difference in the salaries of men and women at this university? Would we see, have crime rates really increased, that type of thing? These are where we normally use p-values. That doesn't mean that there's only a 5% chance that the value we see is due to noise. It only means exactly this, which is really hard to get your head around. It means that if there was no difference, we would see the difference we actually saw about 5% of the time. Right, so it actually doesn't say anything about the hypothesis we care about. It only says something about the hypothesis we don't care about, and the implication goes in the wrong direction. What we really want is the probability that our hypothesis is true given the data. Instead, what we get is the probability that we see our data given a hypothesis that we're not testing. So it's a weird calculation. Now, there is still logic in it, because as I showed you before, if the null hypothesis is very unlikely to have generated the data, then something else did, okay? And if the only other thing that could have done it is the thing we care about, then yeah, when the p-value gets very small, that is strong evidence for our other hypothesis. So let's talk about this. This is, I introduced the idea of a test statistic. This is a measure of like how extreme our result is. So this is a standard formula for the difference in means of two groups with different variances. I'm not going to go into how we derive this, and in fact, I'm going to recommend that you never use this formula. I'm going to recommend that you do it through randomization. In fact, what I'm going to show you is a way to compute a standard statistical p-value without these formulas. So the test that I'm going to show you is, and this, you're going to do homework on this, on exactly this problem, is let's imagine that there's two different classrooms that differ in some variable we care about. Maybe one has a better paid teacher. Maybe one uses different textbooks. And we have the standardized test scores for every student in both classrooms. And we're going to ask, does it matter which classroom they're in? Now obviously the students are not the same, so there's going to be some difference in means between the two classrooms, right? There's going to be some difference in the actual data. But the question we're asking is, how likely is that difference to be something other than just chance? So to answer that question, we have to ask about why we would have those differences. And there's basically only two reasons. There are differences because of differences in the two classrooms, and there are differences because of things that do not depend on the classrooms, like the variation in the students who go into the class. And we have to hope, by the way, that the students are not assigned to a class based on how good a student they are, right? Like that's why we do randomization in experiments. We have to hope that there's no other correlation between classroom and students. But if we think that's true, then what we can do is we can basically break the association between which classroom they're in and their test score through permutation. So this is how we do it. This is what the data looks like. This is the test score. This is which class they're in. And what we do is we randomly reassign the students to classes. We permute the class assignments, or permute the data, same thing, right? We have the same number of A's and B's, but we reorder them. And we do this over and over. In principle, we actually run through every possible permutation. It'll be in the billions. In practice, what we do is we sample a subset of them randomly. And for each permutation, we compute the difference in the means between the two classes. So here's the idea. Here's the original scores for class A and B with the means marked. What we do is we randomly reassign each of these dots to the left or the right, ensuring that we keep the total number of students the same in each class. And then we recompute the means. And you can see sometimes class B comes out higher and sometimes class A comes out higher. We do this thousands of times, and then we look at the difference between the class scores for each one. Is that clear so far? And then we make a histogram of the thing, And this is what we get. We get this histogram of possible differences in the class scores after resampling. And somewhere in this histogram is our observed data. So in other words, this is our real data here. And all of this are simulations of the null hypothesis. And then we ask, what is the probability that we get a test statistic, in this case the difference between the means of the test scores of the classes, that is at least as big as the observed data, at least as extreme as the real data. So looking at this histogram, can anybody tell me how that probability appears on this chart? There is a relationship between this visualization and the p-value. Anybody know what it is? Again, the question is, how often, if the null hypothesis is true, do we see a difference in means that is at least as great as the one that we saw? So what is that on this chart?
So we're looking at all of the buckets that are to the right of the observed difference between classes.
Yeah.
So to the left is about minus 0.15.
Right here?
To the left of that would also be greater differences?
No, that's lesser differences.
Oh, okay.
Right. So this is it, and if we do that calculation, and we're not using any formulas here, we're simply counting the percentage of trials where we get an observed difference at least as big as the real difference, and we get 14%. So that is what a p-value is, and I've shown you one way to compute I've tried to demonstrate two things in this example. One, the concept of a p-value. How often do we get a difference that is at least as great as the one we saw, if the null hypothesis is true? Two, the concept of a permutation test, which is a randomization test, basically a way to use simulation to compute a p-value, where you don't have to work through the analytical formulas of classical statistics. And with a little creativity, you can come up with simulation methods to calculate all of these statistical properties. You very rarely have to actually use the analytical formulas for this type of stuff. So would this be considered a statistically significant difference? Yeah, not by the standard definition of 0.05, right? So this is going to be your homework. I'm going to give you two sets of class scores, or something like class scores, and ask you to compute the p-value through a permutation test.
But since this was created by like random permutations, wouldn't everything that was a greater than 0.15 difference in the other direction also be relevant?
Oh, I see. So yeah, so this is the difference between a one-tailed and a two-tailed test. So yeah, depending on how you think about this, you might want to include all of this stuff too on the left. Because you're asking two different questions. What is the probability that class A is better than class B? And what is as opposed to that the difference is this great by chance? Unfortunately, so I'm showing you this because I'm trying to give you a little intuition about what a p-value is measuring and a way to calculate it for a very standard case. This is mostly what people use p-values for. Unfortunately, p-values answer the wrong question. Let's see, we're going to bootstrap here. I'm not going to do bootstrapping today. So here we are, we're looking at it. This means 0.05, this means 0.01, this means 0.10. And they're like, well, it's not statistically significant, but there's always this problem of threshold. And this is one of the difficulties of p-values, is people want to use them to decide whether something is true or false. But you can't actually decide whether something is true or false. All you can do is weigh the evidence in different ways. Okay? That's what uncertainty is. Uncertainty is irreducible lack of knowledge. emphasis on irreducible. There is no statistical process that you can do that can tell you whether the difference in female assistant professor salaries in the life sciences is due to something, is due to discrimination, right? You can't get that from the data because there is irreducible uncertainty in the data. All you can get is different ways of talking about the strength of the evidence, and the p-value is one way to talk about the strength of the evidence. If the p-value is small, that means the difference is unlikely to have been generated under the null hypothesis, which means that something other than the null hypothesis must be true. It doesn't tell you what. That was the problem we were running into earlier with the statistical tests for tennis fixing. This is a nice paper. It's linked in the syllabus. It's about a bunch of ways that the p-value is misinterpreted. This is the number one misinterpretation. If p equals 0.05, the null hypothesis is only a 5% chance of being true. That's not at all what it says. And one way to see this is to think about writing the probabilities as more formal statements. And so we're going to use this notation. E is evidence. That is what we observe. You can think of that as the data. H is hypothesis. That's what we think of true. This is not quite the p-value because the p-value is at least as extreme, not equal to, but more than. This is kind of what we're doing with a p-value. We're saying, what is the probability of evidence given the hypothesis, given the null hypothesis? What we really want is this. What is the probability of the hypothesis we care about? There's a difference in the classrooms. There's a difference in the pay. The payoff was a cover-up. The match was fixed. There was insider trading, right? That's the hypothesis we care about. Given the evidence that we have, that's what we want. But that's not what a p-value is. And I hope that I have drilled into your head at this point that reversing a conditional probability is completely different. Right? You get these are very different concepts. They're not only different concepts, but I'm actually talking about different hypotheses. And again, it's not that the reasoning is bad, right? So let's go back to the Howland-Will trial. Right? So if it is unlikely that the signatures match because by chance, then it has to be true that they match for some other reason. Okay, the logic is good because we know that the sum of the probabilities of all the hypotheses is 1. So if we can eliminate one hypothesis, it has to be something else. The question is what? And in this case, the only things we're considering is it's forged or it's real. So if it's not real, it has to be forged. Right? If you have only two possibilities, p-values can really work. But in practice, you often have more. Also, the p-value doesn't tell you much about the effect size, which is the thing you actually care about. Right? How much better were the scores, right? Statistical significance only compares against the null hypothesis, which is normally the hypothesis of no effect. So if it's significant, statistically, it may still be a super small effect. So that's this case here, right? Different effect, same p-value, right? So the percent benefit, let's say they're medical trial, right? These both have the same p-value of 0.05, but this is a 2% difference and this is a 20% difference. Right? So the p-value does not measure the effect size. Conversely, you can get this other problem where the p-value is just sort of measuring how accurate your result is. Basically, how many people you had in the trial. Right? We have the same effect size, we just have a lot more uncertainty in when we have a higher p-value. So the p-value is this weird construct that kind of blends effect size and confidence interval, and there's a big movement to eradicate p-values and just have people report confidence intervals instead, because really that's the information you need here. Another way of thinking about statistical significance is, does the confidence interval cross 0? So yeah, unfortunately they mean less than we hope they would. But I'm going to show you an alternative. And I'm not going to go into Bayesian statistics in any great detail, because that's a whole other course. But I'm going to show you foundational ideas in Bayesian inference. And basically it's based on this, right? It's based on, let's back up and represent everything as conditional probabilities. So you're familiar with conditional probability, I hope. This is a fundamental concept. You need to get this in your head or you're going to make bad mistakes. But it's a very simple idea. Really, it's just a definition. It's the probability of A and B happening divided by the probability of A. All right, so we're just taking a denominator. We're talking about two different events, and we're saying, of the things where A happened, how many also had B? And I kind of think of it as this bar as a division sign, and so the A is like, okay, that's the denominator, that's the set we're thinking of. So that's how I want you to think of it. Of the A's, how many had B? Which is not the same as of the B's, how many have A, right? Think of the, you'll see these diagrams in a second. So here's the classic example. Let's say there are yellow and blue taxis in a city, and some of them have accidents, and we're trying to ask which cab company is safer. Now, it should be obvious to you that if you just count the number of accidents, you're going to say, well, the yellow company has more accidents. But of course, there's more yellow cabs. So what we actually want is the rates. And that's kind of what conditional probability is. It's, given that we're yellow, how many accidents did we have? Or in this case, blue, right? So this is what conditional probability is. The thing after the pipe is the denominator, and then we count within that how many had an accident, right? So we only end up counting this accident, not that accident, because this one is inside the denominator. We talked about relative risk a lot a few classes ago. Relative risk is these are the formulas from the contingency tables, but the easiest way to think about it is as a ratio of conditional probabilities. In other words, what is the ratio of getting the disease given that I smoke over getting the disease given that I don't smoke? And I feel like this is a much easier thing to remember. And once you have that, then you can convert this back into the formula of the contingency tables by using these ideas, right? So you should be familiar with converting between this notation and contingency table notation. Hopefully your last assignment forced you to think about that stuff a bit. The base rate, and this is the reason I show you this, is there's a standard error called the base rate fallacy. That's where you look at this data. So when you look at this, it's pretty obvious that the yellow taxis are safer. When you get this data, and you're like, wow, there are many more accidents involving yellow cabs. You have to sort of wiggle this stuff around a little bit to finish the derivation. So I'm turning the numbers that we have into conditional probabilities. So we know the overall probability of an accident. We know the conditional probabilities of having an accident depending on which cab you're in. But we don't know how many yellow cabs there are. oh, actually I've done this wrong. 75 accidents involving yellow cab. This is not, this is wrong. This is just N accident given yellow. These should be N's, not P's. What we actually want are these numbers. And to get those numbers, we need to know the total number of yellow and blue taxis. So another way to think about this is one of these, you need 4 numbers to make this work, right? If you're going to ask which taxi company is safer, you need every entry of this contingency table, because ultimately you're computing this, and this uses all 4 entries. I'm now going to sort of expand on this a little bit into this evidence and hypothesis framework, which is an extremely clear framework for thinking about many statistical problems. So let's say we observe this person coughing, and we want to know, and this is why I introduced the base rate, we want to know whether she has a cold. Let's say we know that most people with colds are coughing. Right, so we know that P coughing given cold is 0.9. What is the probability that she has a cold? We see her coughing. We know there's this link between having a cold and coughing. What is the probability she has a cold?
We need a sense of how frequent colds and coughing are.
Yeah.
Individually.
Right. We are missing the base rates. Okay? So here's the basic issue. We have, again, probability of, we just learned the probability of the evidence given the hypothesis. We have that. We want probability of hypothesis given evidence. So we have to go the other way. The way we get that is Bayes' theorem. Now, Bayes' theorem is not magic. It follows immediately from the definition of conditional probability. It just tells you the relationship between A and B, right? So it tells us that probability of hypothesis given evidence is going to be probability of evidence given hypothesis divided by probability of the evidence, and then divided by the probability of the hypothesis. No, hang on. Times the probability of hypothesis divided by the probability of the evidence. There we go, okay. So in this case, if we translate this out, this is probability coughing given cold times probability cold divided by probability coughing, right? So it tells us how to reverse this. So let's do this. What are reasonable values for each of these things? So we were given coughing giving cold at 0.9. What is P cold? How many people have a cold at any given moment? What fraction of the population?
15%.
15%. How many people are in this room have a cold? Depends on the season.
In the world. But
Or in the world, I don't. You usually have a cold? Okay, what do you want to call this? 5%? Okay. Overruled. Five, yeah, you need to get out more so you can get more colds. What is the probability that someone is coughing? There's one. 10%, okay. 0.1. So what do we get? 0.9 times 0.1 is 0.09, and we get half of that. So was it, divided by 0.1, sorry. We get 0.9 times 0.005, so that's 0.045 divided by 10, okay. Did I do this right? No. There we go. So, okay, 45%. Let's do it this way. Oh, hey, look at that. We ended up with exactly the same numbers. Ha.
Wow.
Yeah. I'm always curious what people will guess. Yeah, exactly. There you go. So there's the calculation worked out in detail, right? And it's not a complicated calculation. The only thing you need is the conceptual machinery to see how all of these numbers relate. Okay? These things have names. So probability of the evidence given the hypothesis, or the data given the hypothesis, is called the likelihood. The probability that you get the evidence at all, where'd I go? Is called the base rate. So how often do I see that data? And probability that the hypothesis is true without any other information is called the prior. Bayes' theorem is also extremely important in interpreting diagnostic tests, such as for mammograms in this example. Or let's say you've got your terrorism detector and someone tells you that if the person is a terrorist and they walk through the scanner, the alarm will go off with 99% probability. But that's not what you actually want. Again, it's the same problem. You don't want the probability that the alarm goes off if they're a terrorist. You want the probability that they're a terrorist if the alarm goes off. That's a significant number, right? So this is the same thing, right? If you get a positive mammogram under this scenario, how likely is it that you actually have breast cancer? And here's the situation, and again, I've borrowed from Nate Silver, and here's the idea, is that the dark squares are positive mammograms and the pluses are cancer, but because cancer is rare, actually most of the dark squares do not have cancer. This is why you do follow-up tests. Right? You get the same thing with any rare disease, right? You get a very similar situation with HIV tests or your terrorism detector. And here's sort of the logic. I'm going to walk through this pretty fast. Again, we have this this is a contingency table in graphical form. And we have these basic quantities, right? So we have the probability that the test is positive if you have cancer. And so this is the easy one to get, right? We can do this. This just depends on the test. We have the probability that it's positive if you don't have cancer. And again, these all have names. So false positive rate, positive predictive value is one set of words. Precision and recall is another set of words, which we think about in information retrieval. In medicine, you use sensitivity and specificity, which I forget how they relate to PPV and so forth. But they're all names for these particular conditional probabilities. And so once you understand the conditional probabilities, you can work with all of this stuff. Here's just the base rates of cancer. And here, it's the same form of problem, right? We know the probability of positive given cancer and some other stuff. We want to know cancer given positive. And you can work and so here you go. We want this piece of the chart, right? Whereas what we're given is this and some other information. So you can work this through. You end up having to compute the overall number, the overall rate of positive. Here's Bayes' theorem at the top. You grind it through, you end up with this 9.6% chance. Right, so there's a lot, most positives are actually false positives. And for your terrorism detector, this is going to be like 99% false positives. There is sort of a philosophy that goes with Bayesianism that is interesting. The idea is that, and so now we've gone from mathematical formalism to epistemological virtue. And the idea here is that we should only believe things for which we have evidence. In other words, evidence is the thing that justifies a belief, which means E is evidence for X if the conditional probability of X given E is greater than just the conditional probability of X alone. In other words, if we revise our probability estimate of the hypothesis upwards when we see that evidence. So that's the formal definition of evidence for something. And the normative part of that is to say that we should only believe things for which we have evidence in this sense. Unfortunately, it's very hard to formalize the world. It only works in a few situations. And again, here's the basic form, right? We start with a model. So this is the model which gives us the likelihood. How often do we cough if we have a cold? And then we start with the base rate. How often do we see that evidence? And we start with the prior, which is how likely is that hypothesis to be true in the beginning. And we end up with this thing which is normally called the posterior, which is how common is the hypothesis given the evidence. And that's what we just did with our example here. Now, this gets arbitrarily complicated when this starts to get things like, what is the probability of pulling someone over given their race? Then we start to have to do much more complicated calculations when we have large amounts of data. And Bayesian inference and statistics is this whole subject. But this is the fundamental formula. This is all we're doing is flipping the conditional probabilities, because we normally have this and we normally want that. This is what a model tells us. This is a simulation, and in fact, I'll show you how this works in a simulation context. So p-values really only talked about the null hypothesis. Bayesian statistics usually talks about comparing multiple hypotheses. So here's a very simple example. Again, this is also in my book. You put a traffic light at an intersection and you ask, did it reduce accidents? So say you're looking at this chart and you're trying to write a story saying, did the traffic light work? So just looking at this data, what do you think? Did the traffic light work? Did it reduce the accidents?
Maybe.
Maybe, good answer. Okay, so to answer this question, what we do is we do two sets of simulations. One is we simulate how many traffic accidents we would get without the stoplight. So everything to the right of the red bar here is fake data. This is simulated data, which means we need a model that tells us how often we get each number of accidents. So in other words, we have a model of the intersection without a stoplight, which is this term that we're computing. Probability of evidence given hypothesis. Hypothesis is no stoplight, evidence is these numbers here. And we have to make up we immediately run into this other problem. We have to make up some definition of reduced traffic accidents. So let's say we'll call the traffic accidents reduced if all of the values after the red line are lower than the minimum of these two values, right? So that means that this one and this one are lower, right? We have to make up some definition of what it, so this is the problem of translating words into numbers. What does it mean to say that the traffic light reduced accidents? Well, we're making up a definition. How we simulate these things, maybe we draw randomly from the history of the traffic data before the stoplight was installed. Maybe we compute the average rate and we use a Poisson distribution and draw from a Poisson distribution. We make some model and then we make fake data and we count how often the data produces the thing we're looking for. And then we make different fake data. Let's say we imagine that the stoplight reduces traffic accidents by 50%. And so basically we take our model and we simulate everything with the number of accidents cut in half. And we ask how often do we see a reduction by our definition. And so in this case it's 1, 2, 3, 4, 5, 6, 7. And then we're going to ask what is the ratio of where we saw fewer accidents to where we didn't. Do I have that? Okay. So what we're actually computing is we're computing the ratio of the probability of hypothesis 1, the stoplight did nothing, to hypothesis 2, the stoplight cut accidents in half. And if you grind through this, what you actually find out is that ratio is equal to the ratio of the prior probabilities, like how much more likely we thought the stoplight would work to begin with, times the ratio of the likelihoods. So doing that simulation, what we get is this term. Okay? We're simulating, so we're assuming the hypothesis. The hypothesis is on the right. We're getting the evidence on the left. We're taking the how often do we see the data, so evidence data, same thing in this case, given our hypothesis. And a little algebra tells us that the ratio of the probabilities of the two hypotheses is equal to the ratio of the likelihoods times the ratio of the priors. So the Bayes factor, the thing we can compute by comparing these two different simulations, you can think of it as telling us what is the strength of the evidence. It doesn't tell us what the overall probability is, because maybe we know that stoplights reduce traffic already. Maybe we know from every other city that when you put in a stoplight, it cuts it in half, in which case this prior would be very high. Or maybe we have no reason to believe that stoplights work, in which case we start with 50-50. Okay? So and this is one of the sort of mistakes of the p-value approach, is that it tries to come to a definitive conclusion. Is this true? Is this not true? Based on only the data we're analyzing and not all the other data in the world. So the likelihood here, you can think of this as incorporating all of the other information we could possibly have. And this is in a sense more honest, because the thing that we can calculate is only what this data that we have right in front of us is telling us. So this is called the Bayes factor. You can think of it as what is the relative strength of the evidence for different hypotheses. And there's no sort of agreed upon thresholds. People don't really use this. There's a Bayes factor of greater than 2, so therefore we accept this as true. The whole concept of accepting or rejecting a result based on a threshold is flawed. As again, we can never reduce uncertainty. We can only measure the strength of the evidence. So here we go. Here's ways of thinking about the strength of the evidence by looking at Bayes factors. And they're saying that and this is kind of a weird table, right? Because what does strong evidence mean? This is one attempt to associate numbers with words. But, by the time this ratio gets up to about 20, which is, about where the standard p 0.05 is kind of set, that we say it's very strong. So the way to interpret a Bayes factor of 20 is it's a model which assumes the hypothesis is true is 20 times more likely to generate the data that we actually saw. That's why I'm tying this back to simulation. Okay, this is a ton of theory. I know I've gone just really rapidly through this. So, any questions about these concepts before we move on? I don't quite believe it. But I will say this. You will, in your career, have to interpret p-values. So you have to understand what they are. But honestly, if you're trying to solve a statistical problem, phrase it in the language of conditional probability, you're going to do a lot better. It's going to be a lot clearer. And if you have to do something that is like a significance test, which by the way I think you shouldn't. By the way, I think you should just look at confidence intervals and effect sizes. But if you have to do something like that, then think about the relative strength of the evidence between different hypotheses. That's one of the problems with the null hypothesis idea, is it only measures the strength of the evidence for one hypothesis, which is the one you don't care about. I want to show you a lovely little interactive here. How many of you have heard of the replication crisis in science?
Can't replicate stuff.
Yeah, it turns out that a lot of published papers, especially in psychology, don't replicate. And, you know, p-values was supposed to prevent this, so why isn't it working? So here, God, I wish I could just get rid of this banner. So here's a lovely little interactive from a long story called Science Isn't Broken, which demonstrates the issues with using statistical significance as a test. And the idea here is, are we going to test, does the economy depend on whether Republicans or Democrats are in office? And what we can do is use different definitions of economics and different definitions of politician, and you know, maybe a couple other factors, right? So if we measure only GDP and we measure only presidents, then no. But if we measure GDP and governors, then yes. Look at that. All right, we got a p-value smaller than 0.5. If we measure stock prices and governors, no. If we measure everybody, anyway, you can sort of see how this works, right? Whether we include or exclude recessions. And you can always find a combination that gives you a high p-value. Again, this is this problem of translating words into numbers. So this is known as the garden of forking paths, meaning that if you change your data analysis, you can get a different significance level. This is a beautiful example of that, and the article is worth reading. So what happened here is the journalist collaborated with a German researcher, a real researcher, right? Actually, you know, worked at a German medical school, and they did a real scientific study with all of the standard protocols of feeding people chocolate and then measuring a bunch of variables. And then they found that the people who ate the chocolate had less weight, had lower weight, to a significance of 0.05. They wrote it up. They published it in a scientific journal, which previous research by this researcher had shown that a lot of scientific journals don't actually read the papers they accept. So, so they got it published in a peer-reviewed journal. Then they sent a press release with a link to the paper to a bunch of media organizations, and some of them wrote stories about how chocolate causes weight loss. So, this is our standard scientific process. They did everything right. It was a real researcher following standard study protocol, publishing in a peer-reviewed journal. This was, and with a statistically significant finding. What was the problem? How did they get this nonsense finding?
With high metals and something else that.
No, totally standard people. They randomized them all. There was nothing wrong with the study design. This was a completely standard study design. So what's the issue?
They chose people who were exercising?
Nope. Nope. Properly randomized. That's one issue. It could be a small sample size, although p-values are designed to correct for sample size. Right? Because think about doing that permutation test. If you have small samples, you're going to get more variance. Right, you're going to get more variance because you're taking averages. And that's what you're doing here. You're comparing the average of the chocolate group to the non-chocolate group. So p-values should correct for sample size. So what is the issue? Anyone know? I did actually say it, but it's Most people aren't trained to look for it. The problem is they measured 20 different variables. So chocolate is going to show an improvement on something. It aids sleep. It lowers cholesterol. But of course, weight loss is the best headline. So this as a name, this is from a paper by Andrew Gelman, who's one of the Bayesian heavies. This has a name in science, which is The Garden of Forking Paths, which is from a title of a Borges short story, which I recommend. You don't have to be fraudulent to get a nonsense significant value. All you have to do is pick a method of data analysis which gives you that value, right? So this is the key idea. Would the same data analysis decisions have been made with a different data set? How do we solve this problem? How do we avoid getting nonsense results just by picking different definitions of what we measure or how we do the analysis? Doesn't this destroy the idea of data analysis? Anybody got an idea of an answer to that one?
Show all possibilities.
Yeah, warmer. Check for correlation. I mean, that's a good idea anyway, yeah. How do we get out of this trap? So I think there's basically two answers. One is statistical significance. The whole idea of statistical significance has serious conceptual problems that we've touched a little bit on today, right? Because you're trying to turn uncertainty into certainty. So use effect sizes instead. Rather than saying, you know, this policy definitely reduced crime rates, say the crime rates fell by 5%, but you know, that's statistical error, so it could be actually anything from an increase of 1% to a decrease of 10%. Right? Find a way to show the uncertainty. And we're still learning how to do this in journalism, to talk about the uncertainty. The other thing is, oh yeah, we saw that. Robustness, which we're just going to have to do this later. Robustness is an idea that appears in a lot of forms. In the social sciences, they call it triangulation. This is a quote by one of my heroes, Charles Sanders Peirce, who appeared earlier in the handwriting example. And what he's saying is that rather than using one type of argument to know if something is true, find lots of arguments. So going back to our hacking our way to scientific glory example, if we got a large effect size, no matter what definition we chose, that's a sign that the result is strong. We say that as a robust result. Okay? What we're looking for are results that don't matter on the definitions we choose, the timescales we look at. And also we want it to be true if we look at different data sets. We want it to be true if we interview people as well. We want the qualitative and the quantitative data to match up. Right? The p-value is asking the wrong question. That's this chart here, right? The p-value is using a statistical model of let's say scientific, but let's say substantive, right? Here's a model of the real world. We think we have students and teachers in classrooms, and we think that if there's fewer students in a class, they're going to get more attention. That is the substantive model. The statistical model is just this permutation test. The statistical model is not the substantive model, right? And if you only draw conclusions based on the statistical model while ignoring what happens in the real world, you're gonna have problems, right? So the p-value will not tell you whether your hypothesis is true or not. It's just one tool in a way to evaluate the evidence. And a strong conclusion will have multiple lines of evidence. All right, that's all we're going to do for today. Thanks, everyone.